Right, so we're gonna continue from where we left off last time, which was about, well, I introduced both of the methods involved with calculating these volumes of solids of revolution, but I didn't, but we only encountered the disk washer method in the homework, and that's mainly because the way that the homework is arranged, it was just made to be kind of simple in that way, where you would have half of them show up being the first method and half of them show up being the second. But as we know, like um, out in the wild, you wouldn't know right off the bat like which method to apply, and so you have to kind of be able to discern from how the problem is structured which method would work, which method you should try to use, which method has a chance of being simple to compute with. Um, so just to revisit this, the disk washer method has these two formulas, this one being the disk one, this one being the washer one. You have to square the radiuses in order to compute like the area of that disk, and then with washer you subtract off the inner disk. With shell method, it's this integral that you would compute, and notice that there's a 2 pi instead of just a pi. That 2 is important. And you have two different functions inside, a radius function and a height function that correspond to the radius and the height of the cylinder that ends up getting traced out. And the idea is that with the additional 2 pi there, 2 pi RH, that's actually computing for you the surface area of the cylinder. And so that's why this equation makes sense, because the integral is going to sum up all of these different cylinders that are all stacked inside of each other, which thus creates that three-dimensional solid. You take the total sum of all of those areas. Okay. I think maybe we'll also talk a little bit about how in the first half of the homework we actually could have done some of these problems using shell method if we were really inclined to. The thing is that for some of them it's a little bit harder to restructure the problem, and in others it's really a pain to do that. So let's see. For this first one, with the red segment being in this orientation, this would construct the disk method. We're rotating about the x-axis. But if we were instead to have the red segment be horizontal instead, what would happen is it would then trace out a cylinder. And so then that would then correspond to shell method. Now, what are the issues that arise with trying to do that, calculate it in that way? Well, notice that if we're varying the red segment horizontal, like when it's laid flat like that, then it's as though we're integrating with respect to the y instead, because the thing is going to vary with respect to y. And notice from 0 to 1, the y is, or the bottom function, the lower function is just the function y equals 0 or x equals 0, actually. But then after 1, it ends up being this line. So then you'd have to actually use two different integrals. You'd have to calculate two separate integrals in order to calculate what that volume would be if we were to try forcing ourselves to use shell method for this problem, which is possible. You could do it. It's just a little bit more of a more work involved. Okay, and 2 is another situation where it's possible. Just involves a tiny bit of work, not as much work as calculating 2 integrals. This one would still be 1 integral. Again, what happens is you'd have to have the red segment be oriented in the other position. So again, in this case, it'd be horizontal. And you'd vary from 0 to whatever the y value is here. But what happens is that instead you'll need to solve the two equations that are given to be in terms of y. They have to be thought of as functions of y, so that you can then actually re-express the integral. And then it would turn out to still be a washer type of problem. You'd have upper function minus lower function. It's just that the functions would be in terms of y instead of x, and yeah, you get to solve. But So this one is actually much more readily like transformable. This one is easier to transform than the first one. Okay. The third one is a bit more tricky. And usually you would like this would kind of be the kind of thing that would tip you off that you shouldn't use shell method for this problem. Because if you wanted to orient the red segment to be in the right orientation for the way that you're revolving the thing, it would be vertical. And you'd notice that the endpoints of the segment are actually lying on the same equation. So you would end up having this red segment that would vary from 0 to 4, as occurs in this problem, but the height of it would be kind of a bit more involved to calculate. Well, here it actually works out to be okay because you could just think about the upper half and you'd realize like that's just the square root function. So you could actually just calculate the length of the red segment necessary. But in general, this would be kind of tricky to deal with. Like if you just had some arbitrary function and then your length is dependent on like two different places along it, is kind of funny way. So this kind of shape is really one where we would really prefer one method over another method. But you can see that theoretically, like both, these methods are still possible. It just amounts to how complicated it could be to calculate, like where you'd have to cut things off at, or calculate these actual lengths. Okay, and four I think actually works out readily fine as well. This would be yeah, no, you can just solve for the things. This one it behaves a lot like number 2. You could just do this in shell method if you really were so inclined to. Yeah. Okay. But I guess let's begin with problems for today, unless anyone has any questions for me. So right. Well, we have these 3 lines that ends up bounding our region, and then we have this y is equal to sine of x squared. So it would make sense to just graph the sine of x squared if you really don't know how it looks like. The closest that you can get to figuring out what it would look like is thinking of it as just the sine function, but distorted along the x-axis. That's x squared is kind of just compressing how quickly you arrive at the x values. So it's like it's compressing the sine function a little bit, and that will distort it. But you can check out how it actually looks if you just plug it into a graphing calculator. And then what you'll get is if we bound it by this x is equal to root pi, we'll see that just this shape is going to the region that we end up revolving. So you can see like if you plug this in, you get sine of pi, which evaluated is equal to 0. So it's actually just the first lobe, I guess, from where the graph crosses 0. So there we have it. And we want to revolve this around the y-axis. Okay. Now, Shaw method says 2 pi on the outside, and then we would integrate this, and then we would have to have a radius function and a height function. Now, first of all, why would we think of this as shell method? Well, the main reason is because if we tried to have our segment be like this, it's rather complicated to figure out how we would even calculate what the length of such a segment would be in general. And so that really dissuades us from that approach. And so we want to use the segment like this. And then revolving this particular segment over the with respect to the y-axis is going to trace out a cylinder. So we know that this is shell method. Okay. And then, well, we know this is going to then vary with respect to x because this line is going to vary from x equals 0 to the root pi. So just imagine that you move that red segment around. Each position is going to trace out a different cylinder. And then we are integrating over all of that. Okay, now what is the radius in this case? Well, this is the simplest situation where the radius is actually just going to be the value x. because and that works out because the axis that we're revolving around corresponds to one of the standard axes. So here we would just say X for that. We don't use the same color. Okay, and what about the height of the cylinder? Well, that's going to correspond to the height of the function, right? So if you, for a particular X value, you would then plug it into the sine of X squared, that would give you the height at that position. And so that tells us this integral will when we evaluate it, will give us the volume. And so then we just need to evaluate this guy. And I'm going to pause here for briefly just to let you think about how you would evaluate this, because you should know how to. Okay, so hopefully you figured it out. So the thing is that this X squared should really remind you of doing a U substitution. You would want to sub away that X squared, and then that tells you du is equal to 2x dx. And notice that very nicely captures the X that is outside of the sine function. And then the last thing is, well, we need to introduce a 2. Well, what's nice is that we already have a 2 lying outside, so we can just push that 2 inside. And so I'm just rewriting the integral to set it up nicely for the U sub. And then performing the U sub, what it's going to do, it becomes sine of U du, and then you have to convert the limits of the integral. Okay, so U is equal to X squared. That means to convert the limits over to the U world, we have to square the values in the X world. So that's going to give us this integral, which we will just compute. So integrating that is going to give us negative cosine of U evaluated from 0 to pi. And then when we plug in, let's see, cosine of pi would be -1. So this will give me +1 to start with. Plugging in 0, we will get 1. So we'll have -1. And so we get 2 pi. Yeah. All right. Any questions on this? Okay. Right. Then next, number 6. This works out pretty nicely as well. Well, really, they all have to. So sine or y is equal to x. That's just this, and then y is equal to x to the 8th power is something like that. And we know that they intersect at 1, and we want to revolve this around the y-axis. So one reason why I'm making it this flat is actually when you try graphing like x squared, x to the 4th, x to the 6th, x to the 8th, what you see happens is that around the interval -1 to 1, it actually flattens out. It's like it stays very flat and then it shoots up very fast. Whereas outside of 1, it grows very fast as you normally would expect. But this is roughly what the shape should look like. Okay, and we want to rotate it. So this shape, you can kind of tell, like if you really wanted to, you could do this using washer method, right? If you wanted to, you could totally choose this as your segment. But then what would happen is you'd have to solve these two equations so that their equations with respect to y instead of x. Then means that you have to integrate like an 8th root, but it's still totally manageable. Okay, but for this, the way that the homework is structured, we probably want to think of this or this orientation instead, and instead choose to use shell method. Okay, but the two are about the same amount of work, I would say. Okay, so shell method now, again, 2 pi on the outside, integrate, and we see that the we would vary the line over the x-axis, so it's an integral with respect to x, and it's going from 0 to 1. Again, the radius for the cylinder is going to be just x. You can just see that from the diagram. And now the length or the height of the cylinder is going to be the difference of the two functions. So it's going to be x minus x to the 8th. Okay, so this is the integral to compute, which we can go ahead and do. So integrating this, we'll get, well, first maybe I should simplify the integral, simplify the inside. So x squared minus x to the 9 dx. Okay, now I integrate this. X cubed over 3 minus x to the 10 over 10, and then evaluate it from 0 to 1. Well, plugging in 0 is just going to give me 0, so I can kind of ignore that. And then plugging in 1 is going to give me a third minus a 10th. 10 minus 3, 7 over 30, 14 over 30 pi, which we would want to simplify to 7 over 15 pi. Okay. Right. All right, let's go to the next problem. So we have x, y is equal to 1. If you don't know right off the bat, you can solve this for one of the variables. Probably you would choose to solve it in this way, and you see that this is the standard parabola, a standard parabola, or hyperbola, sorry, hyperbola. 1 over x. So x equals 0, y equals 1. Let's say that that's around there, and then y equals 5, let's say it's around there. And so this is the region that we're working with, and we're revolving this around the x-axis. Okay. So the way that this is set up, if you wanted to do this like that, that would correspond to washer method. The problem is that you have to compute two different integrals, because the left half, it behaves like a rectangle, but then the right half, you have the hyperbolic piece as the upper function, and the lower function would be the y equals 1. So computing it using washer method would require two different integrals. If we do it instead in this orientation, it's just one integral. It's just shell method. But what happens is we have to consider not this function, but instead we would have to do x equals 1 over y. Because what happens is you can see that the red line is going to vary vertically. It's going to vary with respect to the y-axis. And the integral we would want to set up actually is an integral with respect to y. We want the y to go from 1 to 5. And so that's why everything inside the integral we expect to be with respect to y. Okay. Now let's think. The radius is actually just is still the standard situation, because actually the axis of revolution lines up with a standard axis, the x-axis here. So you can see that like this length, for some given y value, the radius would just be that y value, right? You can see that that's true. But the height now, well, it's going to be corresponding to however it intersects the curve, right? This is this curve. So it's going to be the 1 over y. That'll be the height of the cylinder. And now we just compute this integral. Well, it kind of works nicely. You can simplify the inside. You see that we're just integrating 1 inside, which is going to give us the value y to evaluate from 1 to 5. And so we have 8 pi. So 5 minus 1 is 4, so 8 pi. Okay, questions so far? Okay. Well, then the very last problem here. So this is the more challenging of the problems, I guess, because the axis is now off one of the standard axes. And so what that's going to do is it's going to change the radius function by a little bit, I think, as we will soon see. Now, first of all, how would we graph this thing? So you shouldn't need to reach for a calculator for this, because what you can do is realize that by factoring it, you have this. And that tells you that this parabola intersects the x-axis at two positions, at x equals 0 and at x is equal to 1. And that tells you what the shape of this region is. So we now know this is the region that we're integrating, and we want to integrate this over x equals 3, the line x equals 3. Okay, so now we are revolving that region over, and well, it should hopefully jump out at you to use this as our segment to revolve, which then tells us, again, this is a shell method. 2 pi on the outside. And we want to integrate this with respect to x. And we can see that the red segment is going to vary from x equals 0 to x is equal to 1. I might need a little bit more space inside, actually, but we'll see. Okay. Now, the height function, in this case, is the easier function to list off. That's just going to be the function given to us, x minus x squared. The radius function is where it's a little bit trickier, where we have to think a bit, okay? Because you'll see, like, well, it's not just going to be x in this case. So the first first I'm going to explain, like, in terms of thinking about the extremes of this problem. So the extremes of this problem are like, where are the extremes of placing this red segment? It could happen at x equals 0, and it could happen at x equals 1. And what you can kind of do is consider those two cases and see, like, what happens to the radius function. So at x equals 0, the red segment happening over here, the radius would actually be going from this 0 to 3. So its length, the radius would actually be 3 in this case. In the other extreme, x is equal to 1, you see that the radius function, or whatever the radius function should give out, it should give the value r is equal to 2. And then you can kind of, like, visually scan through this and see, like, as we vary this red segment, imagine, like, it flowing from 0 to 1 constantly with a constant velocity. You can see, like, that the radius function would be decreasing from 3 to 2 with a constant velocity. So that tells you it's actually supposed to be a line, this radius function. And so then from that, you could actually get that the radius function should be the function 3 minus x. This will satisfy all the criteria that we need. But there's actually a, it might feel a little bit hand-wavy to you, this approach, but for me, like, this is kind of the more intuitive. This is more intuitive for me. But here's another way you can think about this. So this, whatever place we put the red segment, the distance to 0 would be the value, the x value, okay? And then, well, the actual radius would be given by this other bigger bracket here, okay? And what you can see is that in total, the two things should be equal to be 3, should be equal to 3. So that tells you that this radius has to be 3 minus x, okay? So I don't know why this doesn't immediately occur to me, but for some of you it might. But yeah, so either way, you can see that you can convince yourself that the radius function should be the function 3 minus x, and then use that to fill in the formula for shell method. And now it just amounts to computing this integral. Okay, so now in this case, this really is not something that U sub applies to. What you have to do for this integral is you have to expand the inside out. Expanding it is going to give you a polynomial. And so let's see, we get 3x minus 4x squared plus x cubed dx. I simplified the middle term. Okay. And now we integrate this. So 3/2 x squared minus 4/3 x cubed plus 1/4 x to the fourth. And then we would evaluate this from 0 to 1. Plugging in 0 is going to give us 0, but plugging in 1 is going to give us a bunch of fractions. And so we kind of need to keep track of them. And then we would have to combine them together. So when you do that calculation, you'll get 5/6 pi as your final answer. Okay. So are there any questions on anything? Okay. Well, I'm going to end the recording.